Today I want to show you a way to fairly precisely cut sheet metal on a budget, producing results like this. There are about 3 cheap ways to cut sheet metal. I'm sure you know about sheet metal shears like these, which are like scissors for cutting thin metal. They have their uses, but they really suck for large cuts, for clean cuts, or for precise cuts. You may also know about wheel cutters like these, which are great for straight cuts of any length, but which can't really turn, and certainly can't cut anything precisely. Then there's nibblers like this drill attachment, which are great for cuts that need to go in any direction. This is what we'll be talking about today. All of these sheet metal cutters work by forcing the sheet between 2 cutting surfaces that close into contact, separating the metal. In shears and wheel cutters, however, this cut simply creates a slit in the material at the cut line. A nibbler, on the other hand, acts more like a saw or a mill in that it cuts by removing material. On this nibbler attachment for a drill, you can see that there's a small little piece that looks like a piston, which reciprocates up and down in a cylindrical housing. That's the actual cutting tool. You can see that the piston-like part is stepped and has a wide part and a narrow part. As the sheet metal moves into contact with the narrow part of the cutting tool, the tool moves down, and the wide part starts to engage the sheet metal. This forces the sheet metal down and into the cylinder, shearing off a very small crescent-shaped piece of metal. The tool reciprocates and repeatedly takes nibbles out of the metal, and that's how it cuts. The cylinder that the tool itself travels in is part of a big sturdy steel post with a slot cut in it for the material to enter. The back of the post is solid, however, which means that you have to move the nibbler around and turn it to make curves, like with many cutting tools. It can also cut side to side as long as there's nothing blocking the rear post, which can be useful for cleaning up edges. Nibblers are pretty much always just a handheld tool, which means that you really can't get good results without a lot of effort. The standard way to get better results out of a nibbler is to make a nibbler table like this one. I've never seen a nibbler table that you can buy, so you really have to build your own. The nibbler is mounted underneath, with a drill attached, and the cutting tool sticks up through the table. This lets you get much better control over the metal as you cut it, but it's still not perfect. Freehand cutting with a nibbler is about as accurate as freehand cutting with a bandsaw. Getting straight lines, getting nice curves, it's possible, I suppose, but it's not fun. To solve this problem, what I do is take a cue from woodworkers. They have a similar issue with router tables, where freehand routing of wood is theoretically something you can do well, but which benefits greatly from the use of templates. I've put a link to this Stumpy Nubs video in the description if you want to learn more about those. Their pieces of wood are acrylic, often about 1/4 inch thick, and interact with a bearing mounted on top of a router bit. Nibblers don't have bearings, but this part here on the nibbler post can function just as well. This part is normally not circular, as you can see here, and that can be a major hassle for using templates, so I filed a circular profile onto one side of the nibbler I used. With that done, all you need to do is make a template for your design, stick it to the metal with double-sided tape, and have at it. It helps to do roughing passes first, so you have lots of room to work, and then go back and clean up the edges to fit the shape you want. For my nibbler templates, I typically use a CO2 laser cutter to cut them out of wood or acrylic. You can also 3D print templates. Either way, You need the thickness of the template to be more than the slot in the nibbler so that the engaging surface actually engages the template. In your software of choice, you take the design you want to cut and offset it towards the interior of the template by the thickness of the engaging surface. I measured mine by actually subtracting the diameter of the cutting tool from the diameter of the engaged surface and halving it. I typically use Inkscape for quick and dirty CAD, and I make my templates by adding a stroke to the design with the thickness of twice the offset amount. I then convert the stroke to a path and break the path apart, retaining only the inner one for the template. If you're using a real CAD program like Fusion 360, you can just use an offset in a sketch. As with any tool, there are limits to what you can do with the nibbler and template. The most obvious limitation is that the cutting tool needs to enter the material from one side. It can't pierce the material like a laser, or a plasma cutter, or water jet, and so if you want to cut closed shapes out of the middle of the material, you need to first drill an appropriately sized hole for the nibbler to fit through. Most nibbler kits come with a small step drill for this purpose. Another important limitation is that, like any tool that operates by removing material, the tool in a nibbler has a definite size, here about 1/8 of an inch. This means you can't cut slots narrower than that size, nor can you get corners with real points, only little inner fillets. A related limitation is the fact that the post that engages the template also has a definite size, and therefore the template itself has to have a corresponding geometry. Inner corners on a template cannot be sharper than that size in any way that matters, as the engaging surface won't be able to follow that surface at all. It also means that you can't cut many narrow features close to each other, even if the spacing between them is big enough for the cutter to cut. That's because the slot in the template has to be even bigger than the cutter, and if the spacing is too small, there won't be any template left. A final limitation is material thickness. If you try to cut sheet metal that's especially thin, it won't cut properly, and will often just bend and get jammed into the cutter instead. You need a material that's stiff enough to resist bending and be cut, and for sheet metal, that usually comes from thicker sheets. I found that 0.1 millimeters was too thin to get good behavior, while 0.5 millimeters was absolutely fine. Well, that's it for today. See you next time.